So this is in chapter 4, exercise 4.1. So we have a function t from R2 to R2 defined by t applied to the vector xy is the vector xx. And the first thing is to prove this is a linear transformation. So let's see. So suppose we have, say, v1 is the vector x1, y1, and v2 is the vector x2, y2. So v1 plus v2 is the vector x1 plus x2, y1 plus y2. So t of v1 plus v2, that's t applied to the vector x1 plus x2, y1 plus y2. But what t does to a vector is to replace the second coordinate with the first coordinate. So this is x1 plus x2, x1 plus x2, which we can write as x1, x1 plus x2, x2, which is exactly t, this is t of x1, y1, and this is t of x2, y2, or I can write that as t of v1 plus t of v2. So the first property of a linear transformation is satisfied. And for the second, t of c times v1, c times v1 is the vector cx1, cy1. So you apply t to this, you get cx1, cy1, which is c times the vector x1, y1. Sorry, this is cx1, cx1. So this is c times the vector x1, x1, which is c times t of the vector x1, y1, or c times t of v1. So the second property of a linear transformation is satisfied. So t is a linear transformation. It has to behave nicely with respect to vector addition and scalar multiplication. So this is part A. For part B, well, let's see. So t of xy is x comma x. So t squared of xy, this means t of xy, which is t of xy is xx. And if you apply t to a vector xx, that's just xx. So you replace the second coordinate with the first, but the second coordinate equals the first. And in general, if t to the n is equal to t, then what does that mean? So t to the n plus 1 of a vector xy is t to the n of t of xy, which is t to the n of xx, which is xx. So, well, which is t of xy. So t to the n equals t for all n. Just because it's such a simple linear transformation. Right. Does that make sense? Is that okay?
Yeah, it's good. Thank you.
All right. And for part C, where we have, again, this is the linear transformation, t of xy is the vector xx. What is the kernel of t? So that's all vectors xy in R2, such that t of xy is 0. That's all vectors xy in R2. What is t of xy? It's xx. So all vectors such that xx equals 0. So that's all vectors xy in R2 such that x equals 0. So if you want to draw a picture, the vectors where x equals 0, just the y-axis. So the y-axis is the kernel of T. And the image of T, this is all vectors x, y in R2, say x prime, y prime, such that x prime, y prime equals T of x, y for some x, y in R2. This is the same as saying x prime, y prime equals xx, because T of x, y is xx. This means this is just a set of all vectors, well, where the first and second coordinates are the same. Right? The image is all vectors x comma x. That's just the line y equals x. So this line y equals x in the plane, that's the image of T. And in fact, if you want to understand how this linear transformation operates, if you take any vector x, y, it gets mapped down onto, vertically down onto the line xx. So xy goes to xx. So this linear transformation is just projection onto the line y equals x. Okay.
Okay, thanks.
Did you want me to do problem 2 also?
Well, actually, we only have time for one more problem, right? So could you do a different one instead
Sure.
of 2? Can you do number 4?
Oh, and that's in that set?
Yes, please.
Okay. So this is exercise 4.4. So we have the very nice matrix A is at 1, 2, 3, 4. And we define the linear transformation T sub A of xy to be A times xy, which is 1, 2, 3, 4 times xy. So T applied to the vector xy would be the vector x plus 2y, 3x plus 4y. Okay. So that's the linear transformation. And we want to compute the kernel, the nullity, the image, and the rank. So the kernel of this is all vectors x, y, such that TA of xy is the 0 vector. That's all vectors x, y, such that TA of xy is x plus 2y, 3x plus 4y equals 0, 0. So this means you have to solve the equations x plus 2y equals 0, 3x plus 4y equals 0. So for example, well, I mean, at this point, we know if you look at the determinant of the matrix of coefficients, 1, 2, 3, 4, the determinant's non-zero. So the only solution is x equal y equals 0. Right? I mean, you can also just solve the equations, but when you solve the equations, this only has the 0 solution. So the kernel is just the 0 vector. That's the kernel, just that 0-dimensional subspace. And the nullity, that's just the dimension of the kernel. The kernel is just the 0 vector. So the dimension is 0. And what is the image of T? Well, the image of T is going to be all of R2, because if I take any vector, RS, let's say, I want to know whether I can solve the equations x plus 2y equals R, 3x plus 4y equal S. And this system of equations always has a unique solution. So for any vector RS, there's an xy where t of xy equals Rx. So the image is the whole plane R2, and the rank, which is the dimension of the image, is 2. And it's also consistent with the theorem that says the dimension of any vector space is the dimension of the kernel, which is the nullity, plus the dimension of the image, which is the rank. And in this case, we're in R2. Dimension of R2 is 2, and 2 is 0 plus 2. So that's okay.
Yeah, I got that. I was just checking my work, but thanks.
Yeah. Okay. So let's see. I just want to, in a certain sense, review the last couple of topics that we discussed, the last couple of topics in the syllabus and on the final exam, which have to do with inner products. That's the first, and eigenvalues and eigenvectors, which is the second. So an inner product on a vector space V is a function. I'm going to write it just like this, from V cross V into the field, the real numbers. So that means that for any two vectors, V1 and V2, the inner product is some real number. And this has to be bilinear. So an inner product has three properties. It's bilinear, which means if you fix one coordinate, it's linear in the other. So for example, CV1 plus V1 prime, inner product with V2, is CV1 V2 plus V1 prime V2. And similarly, if you fix the first coordinate and you look at the second, CV2 plus V2 prime will be CV1 V2 plus V1 V2 prime. That's what bilinear means. It has to be symmetric. So V1 V2 is the same number as V2 V1, and it has to be positive definite, which means the inner product of any vector with itself is strictly greater than 0 for all non-zero vectors. And the standard example in Rn, if you have V is the vector x1 up to, say V1 is the vector x1 up to xn, and V2 is the vector y1 to yn, you define the inner product of V1 and V2 to be the sum of the products of the coordinates, x1, y1, x2, y2, plus dot, 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 plus xn, yn. So that's the usual inner product. And if you took Calc 3 or vector calculus, this was called the dot product or the scalar product, and you use it all the time. And this inner product has many, many, many nice properties. And among other things, it allows you to do talk about vectors in a very geometrical way. So the length of a vector V is what? If you take the inner product of V with itself, that's either 0 if V is 0, otherwise it's strictly positive. So if it's non-negative, it has a square root, and the square root of the inner product of V with itself is the length of V, which is denoted like that. So for example, if you take V equal 2, 1, minus 3, the inner product of V with V is 2 times 2 plus 1 times 1 plus minus 3 times minus 3. which is 4 plus 1 plus 9, which is 14. So the length of V, which is the square root of the inner product, is the square root of 14. So this vector in 3 space has length square root of 14. And we say that vectors V and W are perpendicular, or a synonym is orthogonal, if their inner product is 0. So, for example, in the plane, if we take the vector, let's say this is maybe 3, 1, and perpendicular to it is the vector minus 1, 3, and you can check that the dot product of these two vectors is minus 3 plus 3 is 0. Right? So, in fact, we're not going to use it, but there's a very important inequality called the Cauchy-Schwarz inequality, which says if you take in any inner product space, whenever you have an inner product, the inner product of two vectors, V and W, in absolute value is at most the length of V times the length of W. So in analysis and many other parts of mathematics, this is used all the time. But in any case, this is the definition of the length of a vector, and this is the definition of vectors being orthogonal or perpendicular. So the simplest example of this phenomenon is, suppose you take the standard basis for Rn. So I'll call a script E. That's the vectors E1, E2, up to E sub n, where Ej is the vector with all the coordinates are 0 except the jth. So in the jth place, there's a 1. Everywhere else, the coordinate is 0. So the length of this vector Ej is, let's say, the length squared is the inner product of Ej with itself. And then you take the square root for the length. If you take the sum of the squares of the coordinates, you get 0 plus 0 plus 1 plus 0. There's a lot of zeros in a single one is 1. So the length of Ej is 1. So every vector in the standard basis has length 1. And for I different from j, if you take the inner product of Ei and Ej, you're taking the inner product of two vectors where there's only a single 1 and every other coordinate is 0, but the 1s are at different places. So when you take the sum of the products of the coordinates, you just get a lot of zeros and it adds up to 0. So this basis for Rn is a basis of mutually orthogonal or mutually perpendicular vectors, and each vector has length 1. And in many cases, a basis with that property is very nice. So you want vectors that are mutually orthogonal or perpendicular and have length 1. And in general, we say a set of vectors v1 and so forth, vn, is orthonormal if the length of each vector is 1 and they're mutually perpendicular. Vi, Vj, the inner product is 0 for all I different from j. And there is a nice method. So given any basis for a vector space V, there is a method which is called Gram-Schmidt orthonormalization to construct, so let's call this basis B, to construct from the basis B a new basis that is orthonormal. And a simple way to do this is inductively, but let me just first describe one other property of, or one other geometric thing one can do with a inner product. Suppose I have two vectors, V and W, and I want to decompose V as a sum of two vectors, one of which is parallel to W and the other is perpendicular to W. So I have a vector V, and with respect to this vector W, I want to find the component of V parallel to W and the component of V perpendicular to W. So this component parallel to W, this is sometimes called the projection of the vector V in the direction W. And that projection, so in general, if W is a non-zero vector, the projection of V in the direction of W is a certain, so it's going to be parallel to W. That means it has to be a certain scalar multiple of W. And the scalar multiple is, you take the inner product of V and W, divide it by the length of W squared. So this is the projection of V in the direction of W. This is a very important formula or definition, if you like. And the component of V perpendicular to W, well, this plus this is going to be equal to V. So this vector here is what you have to add to this to get to V. So this vector is V minus the projection of V in the direction of W. This plus this is equal to V. And I claim that this is perpendicular to W. So, so what does it mean for this to be perpendicular to W? It means the inner product of this vector with W has to be 0. So let me compute V minus this projection of V in the direction of W, inner product with W. So by the bilinearity of the inner product, this is the inner product of V and W minus the inner product of this vector in W. And the projection is VW over the length of W squared times W, inner product with W. And what is this? This is VW minus, this is just a scalar. I can take it outside the inner product symbol. So minus VW over the length of W squared, inner product of W with W. With the inner product of W with W, this is the length of W squared. So this in the numerator cancels this in the denominator. Then I have VW minus VW. So this is 0. So this vector really is perpendicular to W, and this vector is parallel to W. So here I've decomposed a vector into a piece parallel to W and a piece perpendicular to W. And so that's a very, very, very nice and important part of the geometry of vectors. And notice also, this is the projection of V in the direction of W. So let me just make this as a little additional remark. If W has length 1, then this denominator is just 1. So if the length of W is 1, the projection of V in the direction of W is just the inner product of V and W times W, this scalar times this vector, because this denominator is 1. So let's see. So there's a very nice lemma that is in the notes. The lemma says the following. Suppose we have W1, W2 up to WK. This as an orthonormal set of vectors in the vector space V. And so that VK plus 1 be a vector in V that's not in the subspace generated by these K vectors. So what that looks like is the following. Here's the vector space V. You have these K vectors W1 up to WK, and they generate a certain subspace. Not all of V necessarily, but a subspace of V. It's all linear combinations of these vectors. And you take any vector VK plus 1 that's not in that subspace, right? So if I take W1 up to WK and VK plus 1, if I look at the subspace that generates, that's going to be a bigger subspace because it contains all of these vectors and it contains this. And I claim I can find another vector WK plus 1, which is going to be a unit vector orthogonal to all of these that generates the same subspace. So I want to say let WK plus 1 be the following vector. I take VK plus 1, and then I subtract from VK plus 1 the projection of VK plus 1 on the vector WI for all of the i's, all the WI's in this set. So summation, I goes from 1 to K. So I take this vector VK plus 1 and say this is W1, this is W2, this is, say, V3. So, or maybe I'll let this be V3. So what is the projection of V3 on W1? It's this. So this is the projection of V3 on W1. And the projection of V3 on W2 that's this. So this is the projection of V3 on W2. So I'm taking the vector V3 and subtracting from it the projections of that on all the different vectors in this set of W's. So that's another vector. And maybe I'll call this WK prime, just, that's WK prime. And first of all, I'm going to claim that WK plus 1 prime is perpendicular to all of the vectors WI in the original set. This is 0 for I between 1 and K. And how do we prove that? Well, let's see. WK plus 1 prime, this is VK plus 1, minus the projection of VK plus 1 on WI. So this is for all I. Summation I goes from 1 up to K. The projection of VK plus 1 on WI is the inner product of VK plus 1 and WI divided by the length of wi squared, but this is an orthonormal set. Each of these vectors is length 1, so the denominator is just 1, times wi. So then we compute the inner product of wk plus 1 prime and some wj. So I'm going to take the inner product of all this with wj. So that's vk plus 1 inner product with wj minus the sum, I goes from 1 up to k, vk plus 1 wi inner product wi wj. And what can we say about that? Well, these vectors are orthogonal, right? The vectors in the set W. So this inner product is 0 if I is different from j. So this is actually what you might call, this is the Kronecker delta, delta ij. This is 1 if I equals j, and 0 if I is different from j. So for all the I different from j, this is 0. The term doesn't appear. So I get vk plus 1 wj minus, and when I is equal to j, this is vk plus 1 wj, wj inner product wj, but this is equal to 1 because wj has length 1. So I'm just subtracting this from itself, and I get 0. So this vector wk plus 1 is orthogonal to all of these numbers in this set. And if I want wk plus 1 to have length 1, I simply let wk plus 1 be 1 over the length of this vector, wk plus 1 prime, times the vector. Because if you take any vector and divide by its length, you get a vector of length 1. It's called a unit vector. So this is a way, step by step, how to create an orthonormal basis from any given basis. So let me start with let me try to do a calculation. So I'll just make it relatively simple, but since I'm making up these numbers, the arithmetic might be a little messy. So for R2, we have a basis, let's say the basis 1, 1, and 1 minus 1. Actually, that's not a good example. I'll make it 2, 1, and 1 minus 1. So these two vectors are linearly independent, so they form a basis. But I want an orthonormal basis from these. So this is my vector, let's say v1. And I want to have a vector of length 1. So I let w1 be 1 over the length of v1 times v1. For the vector v1, the length of v1, the inner product of this with itself is 4 plus 1 is 5, is the square root of 5. So this is 1 over the square root of 5, 2, 1. So the vector w1 is 2 over root 5, 1 over root 5. And again, if you don't believe this is a unit vector, you just do the calculation. The length of w1 squared is 2 over root 5 squared plus 1 over root 5 squared. This is 4/5 plus 1/5, which is 1. So this vector has length 1. Now my second vector, v2, is 1 minus 1. So I let w2 prime, this is going to be v2 minus the projection of v2 in the direction of w1. That's equal to v2 minus the inner product of v2 and w1 times w1. Let's see, what is this? v2 is the vector 1 minus 1. The inner product of v2 and w1, that's 2 root 5 minus 1 root 5. So that's minus 1 over root 5 times the vector w1, which is 2 over root 5, 1 over root 5. So this is the vector 1 minus 1 minus, when I do the scalar multiplication, I get 1 over root 5 times 2 over root 5 is 2/5, and this is 1/5. So when I subtract, 2 minus 2/5 is 3/5, and minus 1 minus 1/5 is minus 6/5. So if I did my arithmetic correctly, W2 prime should be perpendicular to W1. So, and let's just check that. So what is the inner product of W2 prime and W1? That's the inner product of the vector 3/5 minus 6/5 and the vector 2 over root 5, 1 over root 5. And when you do that inner product, you get 6 over 5 root 5 minus 6 over 5 root 5, which is 0. So W2 prime is perpendicular to W1, but it doesn't have length 1. What is the length of W2 prime? If I take the length of W2 prime squared, that's the inner product of this vector with itself. That's the sum of the squares of the coordinates. That's 9/5 plus, 9 over 25 plus 36 over 25, which is 45 over 25, which is 9 over 5. So the length of W2 prime, is the square root of this, it's 3 over root 5. So I let W2 be W2 prime divided by the length of W2 prime. The reciprocal of this is root 5 over 3 times the vector W2 prime, which was 3 over 5 minus 6 over 5. So if I can do my arithmetic correctly, this first coordinate is 1 over the square root of 5, and the second coordinate is minus 2 over the square root of 5. And this vector does have unit length, and it is perpendicular to the vector 2 over root 5, 1 over root 5. So this vector and this vector this is the orthonormal basis that I constructed from the original basis, B2, B. So I started with the basis 2, 1, and 1 minus 1, and using the Gram-Schmidt orthonormalization process or algorithm, I construct the orthonormal basis with these coordinates. This and this. So that's Gram-Schmidt. Any questions about this? So, okay. So I want to talk about eigenvalues and eigenvectors. I mean, imagine we had a linear operator from Rn to Rn, and with respect to a certain basis, maybe the matrix for T would look like, let's say maybe this is R3 to R3. 2, 0, 0, 0, minus 5, 0, 0, 0, 1. And what this means is, well, that's the basis. So suppose you take the standard, suppose this is the matrix with respect to the standard basis, E1, E2, E3. So this means that T of E1 is just 2 E1, right? Or just to make sure you see this, this is T of E1, it's the matrix 2, 0, 0, 0, minus 5, 0, 0, 0, 1. E1 is the vector 1, 0, 0. When you do this matrix multiplication, you get 2, 0, 0, which is 2E1. And T of E2 is minus 5E2, and T of E3 is just E3. So this linear transformation behaves very nicely. If you take the vector E1, it just stretches it by a factor of 2. If you take the vector E2, it stretches it by a factor of 5 and points in the opposite direction. So E1, 2E1, E2 minus 5E2. And the vector E3 just gets mapped to itself, pointing in the same direction. So this linear transformation, if it has this basis, this matrix, it means if you take the basis for the vector space, the linear transformation just stretches each basis vector, but it doesn't rotate it or twist it or do anything strange to it. It might point in the opposite direction, but it still is in a direction parallel to itself. And vectors that have this kind of property are very nice. They simplify linear transformations a lot when you can find them or when they exist. So to formalize this, we say that, we have a linear operator. It's a linear transformation from a vector space to itself. So a linear transformation from V to V, the domain and the range are the same, is called a linear operator. It's just a linear transformation. And we say that a scalar, lambda, is an eigenvalue of T if there is a non-zero vector V called an eigenvector for lambda, such that T of V is just lambda times V. So what the linear transformation does to the vector V is not turn it, twist it, or do anything strange to it. It just multiplies it by a scalar lambda. You have the vector V, and the image is just a vector on the same line through V, in the same direction, in the opposite direction, but just a scalar multiple of V. And it's important to emphasize the fact that an eigenvector has to be non-zero. Eigenvalues can be zero, but the eigenvector for any eigenvalue has to be non-zero. And a general problem, given a linear operator T, find the eigenvalues and eigenvectors and associated eigenvectors if they exist. I mean, there doesn't have to be such a vector, such an eigenvalue, but if they exist, find them. And you might say, well, maybe there are a million of them. Maybe there are infinitely many. But there's a certain limit to how many they can be, because there's the following lemma. So we have a vector, a linear transformation from V to itself. And suppose we have distinct eigenvalues, lambda 1 up to lambda k. So these are pairwise distinct real numbers, and they have, let's say, eigenvectors associated to them, v1 up to vk. So I claim these eigenvectors are linearly independent. So the proof is by induction on k. So of course, if k equals 1, you just have t of lambda 1, t of v1, lambda 1, v1, but v1 is not 0. And any set consisting of a single non-zero vector is linearly independent. The only scalar multiple of a non-zero vector that's zero is when you multiply the vector by the scalar zero. Suppose we have two eigenvalues, lambda 1 and lambda 2, and T of V1 is lambda 1 V1, and T of V2 is lambda 2 V2. So I claim V1 and V2 are linearly independent. How do we prove that? Well, just go to the definition of linear independence. Suppose C1 V2 plus C1 V1 plus C1 V2 is 0. So then T of C1 V2 plus C2 V2, that's C1 T of V1 plus C2 T of V2. But these are the eigenvalue vectors. So this is C1 lambda 1 V1 plus C2 lambda 2 V2. T of V2 is lambda 2 V2. This is the zero vector, so this equals 0. But we also have C1 V1 plus C2 V2 equals 0. If we multiply the second equation by, let's say, lambda 2, and we subtract, we get C1 lambda 1 minus lambda 2 V1 is 0. Lambda 1 is different from lambda 2, so this is non-zero. V1 is not the zero vector, so C1 has to be 0. And if C1 is 0, V2 is non-zero, so C2 is 0. So if you have the eigenvectors corresponding to two distinct eigenvalues, they're linearly independent. So then we would try to prove the general result by induction on K. So assume that if you have lambda 1 up to lambda K, distinct eigenvalues with corresponding eigenvectors, V1 up to Vk, then the set of these K eigenvectors is linearly independent. So now consider K plus 1 eigenvalues and eigenvectors. So suppose you have these eigenvectors V1, V2, Vk, Vk plus 1, and some linear combination of them is 0. If you apply the linear operator t to this vector, t of this will be 0, but t of this is t of C1 V1 up to Ck Vk, Ck plus 1 Vk plus 1. That's C1 t of V1, just using the linearity of t, Ck t of Vk, Ck plus 1 t of Vk plus 1. But t of Vi is lambda I Vi for all I. That's because Vi is an eigenvector for the eigenvalue lambda I. So this is C1 lambda 1 V1, Ck lambda k Vk, Ck plus 1 lambda k plus 1 Vk plus 1. That equals 0. Now I also have this equation. If I multiply this equation by lambda k plus 1, I get C1 lambda k plus 1 V1, Ck lambda k plus 1 Vk, Ck plus 1 lambda k plus 1 Vk plus 1 equals 0. And if I subtract these two equations, one from the other, these terms cancel. And what I get is C1, lambda 1 minus lambda k plus 1 V1, all the way up to CK, lambda k minus lambda k plus 1 VK equals 0. And because the lambdas, the eigenvalues are distinct, these numbers are non-zero. But this is a linear combination of V1 up to VK equal to 0. And by the induction hypothesis, those k vectors are linearly independent. So C1, C2 up to CK, they're all 0. And if they're all 0, CK plus 1 is 0, and we're done. So you can't have more. Whenever you have an eigenvalue, you have an eigenvector, and for distinct eigenvectors, distinct eigenvalues, we get a linearly independent set. If your vector space has dimension n, you cannot have more than n distinct eigenvalues. So that's useful to know. So how do we actually try to find eigenvalues and eigenvectors? So there's like a little general theory you can write as follows. So remember the identity operator, I of v is equal to v for all v. This is the identity operator. So suppose we have a linear operator from v to v with an eigenvalue lambda. So that means there exists a vector v different from 0 with t of v equal lambda times v, which I can write. It might seem silly, but I can certainly write this as lambda, the identity operator I times v, which is the same as saying that t of v, or let me write it like this, lambda I of v minus t of v is 0, or these two things are equal and I subtract, 0 is equal to this, which is exactly the operator lambda times I minus t applied to v. So this linear operator, lambda I minus t, this is a linear map from v to v. There's a vector, non-zero vector v sent to 0. So the kernel of the operator lambda I minus t is not the 0 vector. There's a non-zero vector v sitting in the kernel. And we didn't talk about determinants much except for 2 by 2 matrices. But if you write down the matrix for a linear operator, the kernel is non-zero if and only if the determinant is 0. And by finding the different lambdas for which the determinant is 0, we get the eigenvalues. So I want to do that just in the case of 2 by 2 matrices. So suppose we have T from R2 to R2. So this general principle says that lambda I minus T, so lambda is an eigenvalue for T if and only if the kernel of lambda I minus T is not 0, which is going to be the same as saying that the determinant of lambda I minus T is not 0. So let me take an example. Maybe I'll try and find an example in the book so it's easier to follow when you're studying this. So this is in section 6.2, page 339. I'm looking at the matrix A equal to 7, 5, minus 4, minus 2. So I have my linear operator T sub A from V to V. And if I apply this to a vector xy, so TA applied to the vector xy, it's the matrix A times xy. That's 7, 5, minus 4, minus 2 applied to xy, which is 7x plus 5y minus 4x minus 2y. And so that's my linear transformation. Let me write it down again here. So TA of xy is equal to 7, 5 minus 4 minus 2 applied to xy. This is 7x plus 5y minus 4x minus 2y. And I want to find a lambda such that this is equal to just lambda times xy, which is lambda x lambda y. So I want to find the lambda for which there's a non-zero pair xy satisfying this vector equation. This is exactly the same as saying lambda x equals 7x plus 5y. Lambda y is equal to minus 4x minus 2y. Or if I just rewrite this set of equations, this is bringing everything over to the left-hand side. Lambda minus 7x minus 5y equals 0, minus 4x plus lambda plus 2y equals 0. I want to know, when can I solve this system of equations for non-zero x and y? So a system of two equations and two unknowns has a non-zero solution if and only if you look at the matrix of coefficients of the equations. What's the matrix of coefficients? Lambda minus 7, minus 5, minus 4, lambda plus 2. And if you look at that, in fact, you'll notice this is exactly lambda 0, 0, lambda minus 7, 5, sorry, I bring the 4x over, this is plus 4x. Minus 4 minus 2. This is lambda I is the identity matrix, minus A. And I want to know, when is the determinant of this different from 0? So let's call it whatever this, so this is the matrix for lambda I minus A. The determinant, lambda I minus A, this times this minus this times this. That's lambda minus 7, lambda plus 2, minus 5 times 4. That's, and I want to know, when is that, for what values of lambda is this 0? This is a quadratic equation. This is lambda squared minus 5 lambda minus 14 plus 20 is plus 6 equals 0. And this quadratic factors. This is just lambda minus 2, lambda minus 3. So we have two solutions, lambda equal 2, lambda equal 3. And these are going to be the eigenvalues for this matrix. That means you can solve these equations for x and y when lambda is 2, and there's another solution when lambda is 3. So let's see, when, for example, this is my set of solutions, or that's my set of equations. If lambda equals 2, this is minus 5x minus 5y equals 0. Lambda equals 2, 4x plus 4y equals 0. These are basically the same equation x plus y equals 0, or y equals minus x. So if I take the vector, let me call this v1 equal to whatever x is, y is minus that, x minus x, or x times 1 minus 1. So let me just take the vector 1 minus 1. So I claim this is an eigenvector with eigenvalue 2. So let's just check. If I take my matrix A times the vector 1 minus 1, A is 7, 5, minus 4 minus 2 times 1 minus 1. This is 7 minus 5 is 2. This is minus 4 plus 2 is minus 2. This is 2 times 1 minus 1. So I apply the matrix A to the vector 1 minus 1, and I get 2 times 1 minus 1. And 2 is the eigenvalue. That's exactly the definition of eigenvector and eigenvalue. So I have an eigenvalue 2, and I found an eigenvector that goes with it. What about lambda equal 3? So this is my set of equations. If I solve them for lambda equal 3, I get minus 4x minus 5y equals 0. 4x plus 5y equals 0. So this is basically the same equation, and one solution is x equals 5, y equals minus 4. 20 minus 20 is 0. Suppose I take the vector v2 to be 5 minus 4. My matrix A, again, is 7, 5, minus 4, minus 2. If I apply that to the vector 5 minus 4, let me do the arithmetic and see what I get. This is 35 minus 20. This is minus 20 plus 8. So this is 15 minus 12, which is 3 times the vector 5 minus 4. So if I take the matrix A and multiply it by the vector 5 minus 4, I get 3 times 5 minus 4. And this is my eigenvalue, lambda equal 3. So, yeah. So this is the general method to compute eigenvalues and eigenvectors for 2x2 matrices. Let me do 2 more examples. Suppose I take the matrix A to be 0, minus 1, 1, 0. So that's a simple matrix, relatively simple. I want to compute lambda I minus A. That's lambda times 1, 0, 0, 1. That's the identity. Minus 0, minus 1, 1, 0. So lambda times this is lambda, lambda. And when I compute, I get lambda 1 minus 1 lambda. That's lambda I minus A. And I want to know for what values of lambda is the determinant 0. So the determinant of lambda I minus A is the determinant of lambda minus 1, 1 lambda. This determinant is lambda squared plus 1. And if you're working in the real numbers, this is never 0. This matrix is never 0. So that means there exists no eigenvalue. So not every 2 by 2 matrix has a real eigenvalue. And if you look at this geometrically, what is the operation of this matrix on vectors? If you take the unit vector E1, it's sent to E2. If you take the unit vector E2, it's sent to minus E1. So in fact, this matrix A, 0, minus 1, 1, 0, this corresponds to rotation. Vectors are rotated around the origin by pi over 2 radians, or 90 degrees. A rotation has no eigenvalues, because an eigenvalue preserves the direction. So if you take any direction, it's not going to be the case that A applied to this vector is going to be in the same direction, because A is rotating the vector. So except for a rotation by pi, where a vector goes to its negative, a rotation never has an eigenvalue, and this is the simplest example. So not every 2 by 2 matrix has an eigenvalue. You have eigenvalues only when the quadratic equation you get by computing this determinant has real roots. So let me just do one more example, because these are kind of fun to do. I'm only doing 2 by 2 matrices because when you deal with 3 by 3 or higher dimensional matrices, it's much more complicated. And if we had more time, another few weeks, I could do it, but not in the summer. So we'll do one more example. Suppose I take the matrix, well, my favorite matrix seems to be 1, 2, 3, 4. So for this matrix, which corresponds to a linear transformation from R2 to R2, I want to find the eigenvalues and eigenvectors. So lambda I minus A, that's the matrix lambda 0, 0, lambda minus 1, 2, 3, 4. So that's lambda minus 1, minus 2, minus 3, lambda minus 4. And I want to find the lambda for which this matrix has determinant equal to 0. The determinant of lambda minus A is lambda minus 1, lambda minus 4, AD minus BC minus 2 times minus 3. So that's lambda squared minus 5 lambda plus 4 minus 6 minus 2. And I want to find the roots of that quadratic. So by the quadratic formula, because I don't see the other factors, lambda is minus b plus or minus the square root of b squared minus 4ac over 2a. So this is 5 plus or minus the square root of 33 over 2. So we have these two eigenvalues. So lambda 1 is 5 plus root 33 over 2. And lambda 2 is 5 minus root 33 over 2. So let me try to find an eigenvector for this eigenvalue. So what does that mean? It means I need to find xy such that 1, 2, 3, 4 applied to the vector xy, which is x plus 2y, 3x plus 4y, is going to be lambda 1. I'll just write this lambda 1 x, lambda 1 y. Well, this is my lambda 1. So In other words, lambda 1 minus 2x minus 2y is 0, minus 3x plus lambda 1 minus 4 times y equals 0. I guess I need to write down what is lambda 1. Lambda 1 minus 2, this is 1 plus root 33 over 2, x minus 2y is 0, minus 3x, lambda 1 minus 4, so that's 5 halves minus 8 halves, is minus 3 plus root 33 over 2 times y equals 0, if I did my arithmetic correctly. In any case, now I have two equations and two unknowns. I just have to solve them. So that's a bit of high school algebra I'm not going to do, but that's the method. Wow, okay. Any questions about any of this? What I did today really is very important, and there definitely will be a question on the final where you have a 2x2 matrix and you have to calculate the eigenvalues, and for each eigenvalue to compute the eigenvector and eigenvector.
I have a question.
Okay, that's fine.
So yesterday in the review session, you said there were going to be solutions to the practice exam problems and that you might go over them today. So will they be posted later on today since we didn't do that today?
Oh, yeah, so to the extent that I can work out the solutions and post them, I will do that. I have another class after this, but as soon as that finishes, I'll start writing out the solutions to the review problems.
Okay, thank you.
Right, so I haven't done that. I have to find the solutions for you. Okay, that's it for today then. I'll be back at 7 o'clock. And tomorrow at 9 o'clock, it's just going to be for 1 hour, and it'll just be to answer questions. It'll be like a review session, problem session, whatever, from 9 to 10 tomorrow morning. But just for linear algebra, not for my other class. So it'll just be a linear algebra session. Okay, that's all. Hope to see you later. Bye all.